Matt Madison. Matt is a research scientist with USDA Ag Research Service in Burns. His research is focused on bridging the gap between ecological theory and rangeland restoration by establishing a research program that seeks to, 1, understand the limiting factors controlling rangeland seeding success, and 2, develop seed enhancement technologies that are engineered to overcome specific biotic and abiotic factors that have been identified to cause mortality. Please give Matt, the last speaker, a very warm welcome.
Hey, thank you. I was looking in the audience for Jeremy. I needed to correct a few things. For those of you that don't know me, he's much brighter than I am, so he gave me a lot more credit than I deserve. So I thought I'd start off by sharing that with you, but also wanted to mention, I'm glad I can go last because a lot of the research that I've been doing really builds off, work such as Jeremy's been doing and a lot of the other researchers here. So it's nice, and I think you'll be able to see how this work can relate. I wanted to also recognize our funding sources. We recently required a grant from the Nature Conservancy, as well as Jeremy mentioned, we were able to work together on a grant from the Rangeland Research Program, as well as have been able to work on another grant with the Rangeland Research Program with BYU, and then we're getting funded through a cooperative research and development agreement with Aquatrolls Corporation. And I'm going to briefly go over the justification for this research because I think a foundation's already been laid. People understand, how we're losing sagebrush ecosystems at alarming rates. One of the ways is through catastrophic wildfires that essentially leave the landscape looking like a moonscape. And after a severe disturbance such as these wildfires, the site is not able to recover on its own. When that happens, it can transition to a state of annual weed dominance, such as shown in this photo of the cheatgrass covering the landscape, which further degrades ecological processes. And so land managers, they recognize this degradation that's occurring, and in an attempt to restore ecosystem function and processes, they'll go out and reseed. If they have a successful seeding, they can prevent those annual weeds from coming onto the site. The problem is we've talked about it today, in our more arid regions, and particularly if we're using a lot of native species in our seed mixes, our success rates can be extremely low. So land managers are calling for researchers to develop new technologies and techniques that will improve the success of their restoration efforts. There's a variety of things that can limit seeding success, and we've touched on some of them today, such as soil crusting, freezing temperatures, competition from weeds, drought, soil water repellency, saline and sodic soils, predation, maybe even infertile soils. But the limiting factors impairing establishment generally have their greatest impact during the early stages of plant development. And I think this is something that's common among most sites. It's during that early stage of plant development. So therefore, restoration practices that can avoid or improve tolerance to limiting abiotic and biotic stresses during early stages of plant development should have a higher likelihood of success. That's where we're using seed coating technology as a way to address this. Seed coating, or I'm calling it seed enhancements, as an umbrella to encompass not only seed coating but encrusting and various other seed technologies such as priming. But these technologies have the ability to physically manipulate the seed and improve seed germination, emergence, and early seedling growth. It's our working hypothesis that restoration success can be improved by applying seed enhancement technologies that are designed to address specific barriers limiting plant establishment. Today I'd like to share with you 6 technologies that we're working on. I'll just go over them briefly, but they have potential, we feel, for increasing soil water availability, improving emergence and crusting soils, enhancing plantability of small seeded species, controlling the timing of seed germination, improving seed-soil contact of broadcast seed, and lowering competition from weeds. The first technology I'd like to share with you is that we've designed, or it has application for in the pinyon juniper woodland, but also has application for other areas that are limited by soil water repellency. Pinyon juniper woodlands are a system in particular that are where water repellency is a common occurrence, even prior to the fire, which some people don't realize. We've done some work where it appears like that water repellency may in fact be may be beneficial for the plant. One of the reasons why that might be is so during a precipitation event, that water repellency helps transfer moisture via bypass flow or finger flow through select wet patches down deeper into the soil profile. It's down there by the roots, and that water repellent layer can act as a cap, so to prevent evaporation loss. Now during a fire, litter material, organics at the surface, as well as these hydrophobic material in the soil can volatilize. It's heavier in air. It goes down to the soil, hits those cool underlying layers, and then condenses back out, coating the soil particles, often creating a more enhanced or more severe water repellent layer. I want you to think back of that the slide I was showing with the airplane coming across throwing seed down. And the seed lands on this soil condition. The amount of moisture that's available for that seed is essentially contained within a thin, shallow layer. Oftentimes we'll have a wettable layer or an ash layer there, a centimeter or so thick, and then we have our water repellent layer going like this. I like to catch big fish and stuff, but it's actually about 10 centimeters or so thick. But it is disconnecting that seed from those underlying moisture layers and creates a very dry, erosive environment. Now to change gears a little bit, in the golf course industry, the application of soil surfactants is a best management practice for treating soil water repellency. That's something people don't often correlate water repellency with turf grass. You may have noticed it in your lawn. You'll get a patch that it dries down and you pour water on it, it just runs off. You can't get it to green up. One of those, oftentimes that can be water repellency issues from root exudates, decomposition of organic matter and so forth. And here this slide shows a trial that Aquatrolls did in the Netherlands on a golf course. They sprayed half of the green with a soil surfactant. You can see how it was highly effective in overcoming water repellency and improving turf grass performance. Now, here's a neat technology for treating golf courses, but it's just not really practical to apply these surfactants across large land areas in rangeland conditions that have relatively low economic value. So to overcome that problem, what we've done is we've coated seeds with this soil surfactant. In this way, the seed is the carrier for the surfactant. Precipitation can release the surfactant from the seed into the soil where it ameliorates that microsite surrounding the seed. This creates a wet patch, if you will, and more importantly is connecting that seed or seedling with the underlying moisture reserves to help improve plant establishment. And I've put a couple of our publications on the left-hand side. Interestingly enough, we're getting interest from the turf grass industry to try these surfactant-coated seeds there. So they may have application for rangeland as well as turf grass. This is a trial we recently completed in a burned, highly water-repellent pinyon juniper woodland just south of St. George, Utah. The study plot was actually just on the Arizona border, fairly dry environment, and I've kind of summarized the data here. Where basically the treatments that we're looking at is a control, so no coated seed, and then a coated seed, which is our surfactant seed coating. I've labeled that or designated that on this graph as SSC. And in the first spring after planting, we had about a threefold increase in a number of seedlings that emerged. And then after this period, it was fairly drought conditions. We were receiving about 60% of normal precipitation, and there was quite a bit of mortality that occurred at the site. But one of the positive things is that the surfactant-coated seed maintained elevated plant densities over the control. And in this site, you might could say that success could be considered about 1 plant per meter squared. And one of the things that we did achieve here is that with the surfactant-coated seeds, it was, call it, successful with that standard, whereas the control failed to meet management objectives. So they're not great results, but I think it's a positive result. Next, let's kind of slid over, but maybe this is why I should have saved it in the earlier version. but anyway, I want you to look at the soil physical crust here, and that's what I wanted to show. As Jeremy talked about earlier today, seedling emergence represents a major developmental bottleneck in the progression from seed to established plant. And he also talked about how we were really brilliant in developing a solution for overcoming this problem. And I'd like to clarify that as well. So in the seed coating industry, a significant amount of effort goes into trying to keep the seeds from clustering or clumping together. And if you don't know what you're doing, you end up with these clumps or agglomerates. And being the novel seed coaters that we were when we first started out, that's all our batches that keep just agglomerating or grouping together, and we kick the coater and everything else. But then after a while, we got to thinking, is there something that we can do with these? And we hypothesized that, well, maybe multiple seedlings planted in the same location should generate greater emergence force than a single seedling. And we found that is in case true, and we were able to get better emergence when those seedlings are clustered together. And that research has started about 4 years ago, but that's kind of led us down a path where we've been looking at various other technologies where we can try to clump or cluster seeds together. Another interesting finding with this is that we knew that, or we did hypothesize that we'd get better emergence because they'd be working together, those seedlings, but they're also occupying the same niche. So there's interspecific competition would be high. And something that's been has been counterintuitive to me is that we're seeing that we can get better growth or plant bigger when they're clustered together. I'm not going to share a lot of data with you on this, but I've talked past this slide, but let me back up a little bit. This slide here shows a seedling emergence from a greenhouse trial. And the squares, dark squares, they represent the agglomerated treatment. The triangles is where we coated seeds with the same material but didn't agglomerate them together, and then the round circles represents the control. And what we found is that the agglomeration treatment had a earlier emergence as well as a longer period of emergence. And by the end of the study, we had double the number of seedlings that had emerged. This data also indicates that the coating we used also provided some benefit. But back on the topic of plant vigor, something that we've been seeing in the greenhouse and in the field is that these seedlings that are coming up in clusters appear to be more vigorous, if you will. They're more robust. And we've seen some indication it's not extremely high, but on a per plant basis, we see a little more